Okay, the next diagram to calculate is this one, where we have one vertex, and that's a new vertex, and that vertex factor we found here, this one. This is the vertex factor, and then there is the loop contribution. There is only one propagator because there is only one vertex here. The symmetry factor is half, and then ddl 2 pi to the power d 1 over L square plus M square. And that's just I1 D and A is equal to 1. So the result will be minus 3 lambda mu to the epsilon 1 over epsilon plus G1 3 by 2. I1 D comma 1 is given by M squared to the power D by 2 minus 1 divided by M square divided by 4 pi to the power D by 2 gamma 1 minus D by 2 by gamma 1. Writing in terms of epsilon, this is 4 minus epsilon, so 2 minus 1 is 1 minus epsilon by 2 divided by 4 pi to the power 2 minus epsilon by 2 gamma 1 minus 2 plus epsilon by 2. So minus 3 by 2, just like before lambda and 4 pi square, this combination makes it lambda hat square mu to the power, well, mu to the power epsilon will go 1 per epsilon plus G1. This is M square divided by 4 pi to the power minus epsilon by 2, which is M square divided by 4 pi mu square to the power minus epsilon by 2 gamma minus 1 plus epsilon. This is M hat square to the power minus epsilon by 2, which is e to the power minus epsilon by 2 log M hat square. So 1 minus epsilon by 2 log M hat square plus ordered epsilon square. And gamma minus 1 plus epsilon by 2 has to be expanded with this formula where n is 1. Minus 1 plus epsilon by 2. So n is 1. So that is a minus 1 factor, 1 over epsilon plus psi 2. So this is minus 1, 1 over epsilon, which is 2 by epsilon plus psi 2 plus ordered epsilon. That makes 3 by 2 lambda hat square 1 over epsilon plus G1 times 2 by epsilon plus psi 2 plus order epsilon 1 minus epsilon by 2 log n hat square plus epsilon square. Again, my the maximum pole is 1 over epsilon square, so that is 3 by 2 lambda hat square, 2 by epsilon square. Then 1 over epsilon terms. 1 over epsilon psi 2 1, that combination will give you psi 2, and g1 2 over epsilon 1 will give you 2g1, and 1 over epsilon 2 over epsilon, and this will give you minus log m hat square plus order 1. So our result is given by 3. I might have missed a factor of m squared somewhere. Yes. Yes. So we had m squared to the power 1 minus epsilon by 2. And this 1 m square factor has been missed. So let me put that back in. Then it's 3 m squared lambda hat squared times 1 over epsilon squared plus 1 over 2 epsilon times minus log m hat squared plus psi 2 plus 2g1. So this is the result. So after calculating these two new diagrams, this one and the previous one here, we should now add all the 4 diagrams in the that contribute to the 2.1 pi at order lambda squared. So let's do that. And we should use the results for the first 2 diagrams. We should use the results that we already obtained earlier. So let me quote from here. I have written them down. sorry, the first one I copied it wrong. This is not the result. This is one loop result. This is the two loop result. This is this double scoop diagram. And then setting sun diagram is this one. And then the new result that we found here and the last one is this one. Now, one can easily see that between the first and the third diagrams, the double poles cancel. This term and this term are same with opposite sign. That's because that if you take this diagram, then it is the sub diagram. This is the sub diagram. That sub graph that was precisely getting cancelled. This extra additional vertex, this is one. This vertex was we got this vertex by making sure that it cancels this diagram. So it is cancelling that part, but that comparison doesn't work for the second and the fourth diagram. They have different topological nature, which is why the second and the fourth double pole, they don't cancel, but the first and the third do. Okay, so let us now calculate this. Now, this is a straightforward calculation. So I have done this calculation here. So let me just quote this result. So you can just write down all the terms and then simplify. So these two terms, psi2 minus psi1, gives you one that you can check. In fact, there is a more general relation, psi n plus 1 minus psi n is equal to 1 over n. So this is for n equal to 1. We have that, and that combined with minus 3 gives you minus 1. So the result would be, so let me quote that result also. This is the result. One should check if this result is right. In fact, one should check all these calculations that I have been describing if there are errors. So this minus 1 is coming from this psi2 minus psi1 minus 3 from that. So this is the result. Now, so let me write this order 1 contribution to be give it a name, say f2 m hat square, which is order 1 contribution, and then order epsilon. So that's the final result, and this implies that one needs, since that after adding all the contributions to the 2.1 pi at order lambda square, one still is left with poles in epsilon. So therefore, we need additional diagram at this level. And that would be given by a new vertex at lambda square, at order lambda square, which is where we have just the opposite poles. Now, there are two types of terms here. One is poles appearing in mass terms, mass square, and the other pole is appearing with momentum square. So these are, if we have to produce the corresponding counter terms, counter term Feynman diagrams, then the Lagrangian for these terms and these terms will be different. So because P comes from a derivative of the scalar field phi, m square, the mass square counter term will just be phi square. So we therefore have to have two different, in the counter term diagram, we can have two different finite P ambiguity. So this new diagram therefore should look like the following: lambda hat square by 12 epsilon, or say lambda hat square times P square 12 epsilon plus a finite ambiguity H epsilon comma m hat square, and the mass square term is lambda hat square m square with a minus sign 2 over epsilon plus 1 over 2 epsilon times 2f1 plus 6 g1 minus 1. Plus finite ambiguity. So both these two terms are finite as epsilon goes to 0. This would imply that the net diagram 2.1 pi up to order lambda square will be given by at order lambda and the new vertex. This one is given by, as we have calculated, lambda hat m square times f1 m hat square minus capital F1 0 m hat square. And this contribution will be lambda hat square p square times h 0 comma m hat square plus lambda hat square m square times f1 hat square minus sorry, f2 mx square minus f2 0 comma mx square, which is the total contributions. All of these terms are finite. Both this order 1, order lambda, and order lambda square results are finite, though there are ambiguities. These capital F's are the finite ambiguities in the counter terms, and the corresponding Lagrangian counter term Lagrangian will look so let me write down here. So corresponding counter term Lagrangian will be, for the momentum dependent term, this one will be produced by a term minus half del mu phi times lambda hat square 1 over 12 epsilon plus h2 epsilon n square. Since it is at lambda square, let me call it h2 instead of h. And the mass counter term will be given by half m square phi square times lambda hat at order lambda hat. We earlier calculated it, and at order lambda hat square it's given by 2f1 plus 6g1 minus 1, or rather here 2f1 plus 6g1 minus 1. That's a mass counter term. And we earlier calculated the phi-4 counter term, the interaction. Let us go back and check. So this is the term 3 by epsilon plus 3g1. So this is bringing the theory, rendering the theory finite up to order lambda square.